Welcome students. Today we are going to start class 9 science chapter 4 structure of atoms. As in this chapter we are going to discuss about the subatomic particles, that is electron, protons, distribution of electrons, systematic atomic structure, valency, and also the atomic number, atomic mass number, and the notations of the elements. We will also cover the isotopes and isobars. As we all know that electrons, protons, and neutrons are the subatomic particles of an atom. If we remember chapter 3, that is atoms and molecules, which are basically the fundamental building blocks of a matter. So different kind of atoms combine together to give us different kind of substances. As per the Dalton atomic theory, an atom is indivisible. So we can say that from the various of experiments that an atom consists of 3 subatomic particles, that is electron, proton, and neutrons, which is having a smaller size than an atom is present. So we can conclude that an electron is discovered, or we can say invented by Ch4 Thomson. This is the main consequence of a particle in an atom. The electrons are indicated with E negative sign, means small e with a negative sign. This negative sign indicates that the atom or the electron carrying a negative charge, that is your electron, and the charge of electron is -1. Mass of an electron is negligible. So we can say it is approximately equal to 1/2000 of a mass of a proton. Now, what is proton? Basically, protons are positively charged particles. It was discovered by E. Goldstein in 1886. These particles, which having a positive charge, are named as protons. Protons are indicated with P positive sign, and the positive charged particle is known as proton. The charge is equal to +1. The mass of proton is 2000 times to that of electron. This mass was taken as 1 unit. Neutron. Neutron is the third subatomic particle. Basically, it was discovered by J. Chadwick in 1932 as a third important subatomic particle, that is neutron. Neutrons are indicated with a small n alphabet. It has no charge. So we can say the charge of neutron is 0. Mass of neutron is slightly greater than the mass of proton. It was also taken as 1 unit. Now, let us have a comparison between electron, proton, and neutron as per the different properties. First property is discovery. So electron was discovered by Ch4 Thomson, proton was discovered by E. Goldstein, and neutron are discovered by James Chadwick, or we can say J. Chadwick. Second property indicated over here is symbol. Symbol means electron represented by small e, proton represented by small p, and neutron represented by small n. The third property is your nature. So to compare that, we can say that electron is negatively charged, proton is positively charged, and the neutron is neutral. The relative charge is your fourth property, in which we can say that electron is -1, having the charges -1, whereas proton is +1 and neutron has no charge, that is 0. Now, if we calculate the absolute charge on electron and proton and neutron, so we can say the absolute charge on electron is 1.602 into 10 raised to power -19 coulomb. Whereas in the proton, it is also the same. It's 1.602 into 10 raised to power -19 coulomb. Whereas neutron has no absolute charge. The relative mass, the relative mass of electron is approximately 1 upon 1837, which is approximately equal to 2000. That means 2000 mass as compared to proton. And for neutron and proton, we can say the relative mass is 1 unit. Relative mass is 1 unit for protons and neutrons. And the absolute mass, if we are going to talk about the absolute mass of electron, protons, and neutrons, we can say that the absolute mass for electron is 9.109 into 10 raised to power minus 28 grams, whereas for proton, it is 1.6725 into 10 raised to power minus 24, whereas for neutron, it is 1.6748 multiplied by 10 raised to power 24 grams. So this is a comparative study of electron, protons, and neutrons as the subatomic particles of an atom. How are electrons distributed in different orbits or the shell? So the distribution of electrons was into the different orbits was given by Bohr and Bury. According to him, they have given some rules that the maximum number of electron accommodated in a shell is 2n square. So the maximum number of electrons accommodated in particular shell is given by the formula 2n square. So we have a shells K, L, M. So the number of electrons accommodated in the K shell is given by the value of n is 1, for L it is 2, for M it is 3. So we have a formula 2n square, that means 1 square is equal to 2, whereas 2 square is equal to 8, and again n is 3, we will get 18 electrons. Another last one is n. In L shell, the 2 and the value of n is 4 square, which is equal to 32. So we can say that in K shell maximum 2 electrons can accommodate, in L shell 8 electrons can accommodate, in M shell 18, and in N shell 32 maximum electrons are accommodated. Now the second rule is that the maximum number of electrons can be accommodated in each shell is 8. Third is electrons are not accommodated in a given shell unless the inner shells are completely filled. First we have to fill the inner shell, then we will reach to the outermost shells. So on this basis, if we have to distribute the electrons, we can do distribution of electron from 1 to 20 elements. Now if we see the distribution of electrons by first 1 to 18 elements. First element is our hydrogen. The atomic number of hydrogen is 1. It indicates that the distribution of electrons, first it will go to the inner shell, that is 1 electrons. Now if we have helium as a second element, so the atomic number of helium is 2. So the 2 electrons will accommodate it at K shell. So K shell accommodate maximum 2 electrons. After that we have lithium. The atomic number is 3 and the distribution in K shell is 2 and 1 is in your L shell. So in this way we can continue with the first 18 elements. For example, now if I take carbon as C, the atomic number of carbon is 6. So if now we have to distribute the electrons K, L, M and L shells. So 2 electrons are accommodated at K shell. Out of 6, 2 is in the K shell and the remaining 4 will go on the L shell. I'll take one more example such as neon. The neon as a symbol is Ne. The atomic number of neon is 10. So that means 2 electrons in the K shell and 8 electrons in the L shell. So L shell accommodate max. Let's take one more example of sodium. As we know, the sodium is represented by capital N and small a. The the atomic number of sodium is 11. So the distribution of electron in K shell it's 2, in L shell it's 8, and in M shell it's going to be 1. So in this way, the K shell and L shell are now completely filled. Last example, I'm going to take it of sulfur. So the sulfur represented by S is atomic number is 16. So now the distribution of electrons in K shell it's 2, in L shell it's 8, and in M shell it is 6. So in this manner, you can complete this table of first 18 elements distribution of electrons. Now we are going to study. For the atomic structure, we have taken the hydrogen. The atomic number of hydrogen is 1. So the number of electrons are going to be accommodated in the K shell, it is 1. So it is going to be represented by this. In the center we have a nucleus and the K shell has only 1 electron. Similarly, we have helium. In the helium, the atomic number is 2 and 2 electrons are going to be accommodated in the K shell. Now, if we see the lithium has atomic number 3. So, the number of electrons accommodated in K and L shell is 2, 1. Means the nucleus, the outer circle, first circle, inner circle is known as K shell, which has 2 electrons, and in the L shell, which has 1 electron. So, from hydrogen to helium, lithium, we have 1 more shell. And similarly from lithium to sodium, now there is a presence of 1 more shell, that is K, L and M, because atomic number of sodium is 11. So 2 electrons in the K shell, 8 electrons in the L shell, or M shell has 1 electrons. And once the K and L are completely filled, then it will reach to the M shell. Now let us discuss the one more example of oxygen. You know what is the atomic number of oxygen? Atomic number of oxygen is 8. So in the K shell it accommodates 2 electron and in the L shell it accommodates 6 electron. So are you able to see that in the K shell there is a presence of 2 electrons and in the L shell it's 1, 2, 3, 4, 5, 6. Now the next example I'm going to take, that is argon. In argon, we know that the atomic number is equal to 18. So, the distribution is K, L, M. That is 2, 8 and 8. This will indicate that the K shell is completely filled, L shell is completely filled, and then the electrons will go on the M shell, which is also have 8 electrons. Means 2 in the K shell, 1, 2, 3, 4, 5, 6, 7, 8 in the L shell, and in the M shell 1, 2, 3, 4, 5, 6, 7, 8. So this is the basically representation. Your distribution of shells K, L, M is basically represents the atomic structure of an atom. Now we are going to discuss about valency and valence electron. If we see that the hydrogen, in hydrogen the atomic number is 1 and a K shell has 1 electron. So the valence electrons mean the number of electrons present in the outermost shell. So the hydrogen has 1 valence electron. Lithium also has 1 valence electron. Boron has 3 valence electron. Nitrogen has 5 valence electron. Neon has 8 valence electrons. Whereas magnesium has 2 valence electron. But to calculate the valency, we have to know that valency means the combining capacity of an element to accommodate or complete their octet. If we look at the hydrogen, in hydrogen the K shell has 1 electron and the atomic number is 1. So by gaining 1 electron, it can complete their octet to the 2 and it is completely filled orbit and it become more stable. So we can say that the valency of hydrogen is 1. But if we see the case of helium, in helium it has already 2 electrons in the K shell which is completely filled. So it is not required by helium to gain or lose any electron because it is completely filled. So the valency is 0. But if we take the case of lithium, the lithium has atomic number 3.
and the distribution can lose its one electron. It have completely filled K shell. So by losing one electron, it comes to the completely filled shell. So the valency is 1. In the same manner, if we see the other one, we have 2, 3. By losing 2 or 3 electrons, the element can accommodate the completely filled orbit. So the valency is 2, 3. So from 1, 2, 3, if the valency is 1, 2, 3, it means the element is able to lose their electrons and have completely filled orbits, and that is called, they have a valency of 1, 2, 3. But in the case of 4, that is your carbon, the carbon has atomic number 6 and the K shell has 2 electrons and L shell has 4 electrons. Now in this case, the carbon can't lose the electrons or can't gain the electrons. So they have the property that they can share electrons. So we can say that the valency is 4. Now let us take the case of nitrogen. In nitrogen, the atomic number is 7. So the distribution of electron is 2, 5. That means they have 5 valence electron in the outermost shell. And they require to have 8 electron to complete the octet. So what will happen? 8 minus 5 means number of maximum electron accommodated minus valence electron, we will get the valency, that is 3. So we will get 3 valency. By gaining 3 electrons, the nitrogen can complete their octet. So the valency is 3. Similarly, we have a case of oxygen. In oxygen, the atomic number is 8. So the distribution is 2, 6. If we gain 2 electrons, they can complete their octet. And that is why we can say that 8 minus 6 is equal to 2. So the valency is 2. Means maximum number of electron accommodated in a shell minus valence electron to give you valency. Last, we are going to take the case of neon. In neon, the atomic number is 10. So distribution is 2, 8. That means already we have complete octet. The valence electrons are completed in the particular shell. That is 2 and 8. So there is no requirement of any extra electron to be gained or to be donated. So the valency is 0. So in this way, we can say that the valency first increase 1, 2, 3, 4. Then it will decrease 3, 2, 1, 0.
Now let us discuss the atomic number. Atomic number basically defined it as the number of protons present in a nucleus of an atom. So we can say that an atomic number of an element is the number of protons present in the nucleus of an atom of that element. And it is denoted by capital Z. It is denoted by capital Z. All the atoms of an element will have same number of protons. Same number of protons. We have hydrogen, the number of proton is 1. So the atomic number is 1. For the helium, number of protons is 2. So the atomic number is 2. And for the lithium, the number of protons is 3. So we can say atomic number is 3. Mass number. The mass number is basically calculated as the sum of protons and neutrons present in a atom. So the mass number we can define as the sum of the number of protons and the neutrons present in the nucleus of atom. Mass of an atom is almost equal to the mass of protons and neutrons in the nucleus of an atom, as mass of the electron is negligible as compared to that atom. So if we have to calculate the mass of carbon, for the carbon, the mass of carbon is 12 because the number of protons and neutron is equal to 6. Whereas if we have to calculate the mass of aluminium, the atomic number of aluminium or the number of protons of aluminium is 13 and the neutron is 14. So 13 plus 14 is 27. Notation. What is notation? Notation is basically presentation of an atom with respect to their atomic number or atomic masses. So if we have to calculate the or have to write the notation of an atom, first of all, we have to write the symbol at the middle. For example, it is capital X. Now, for that, for writing the atomic number and atomic mass, we use the notations. For atomic mass, we will use the notation for hydrogen atom, helium atom, and any other. So we can first write, suppose for hydrogen atom, the atomic number for hydrogen is basically 1. So we will just write 1 at the bottom, and the mass number is 2. And the mass number is 1. So we can write the notation in this form, 1 hydrogen 1. Similarly, if I have to write for helium, we will write first the symbol of helium, then we will write the mass number of helium is 4 and the atomic number of helium is 2. In this way, we can represent the notation of an atom. Carbon is carbon, a symbol we will write at the middle. At the top, we will write the atomic mass, that is mass number 12. And at the bottom, we will write atomic number 6. Now, what do you mean by isotopes and isobars? Isotopes and isobars are very important compounds, or we can say very important for the atoms. Isotopes are that atom which having the same element having the same atomic number and different atomic masses. Isotopes. Isotopes are the atoms of same element having same atomic number but different atomic masses. For example, if we take the case of hydrogen, hydrogen has 3 isotopes. Hydrogen has 3 isotopes. First isotope is known as protonium, second is deuterium, and the third one is tritium. If you see that all 3 isotopes have same atomic number, 1, 1, and 1. But their atomic masses are different. For protonium, it is 1 because neutron has 0. For deuterium, it is 2 because the number of neutron here in deuterium is 1. And for tritium, the number of electron is 2. So we have different atomic masses, but same atomic number in the case of hydrogen. So they are considered as an isotope. Another example, we will take of carbon. There are 2 major isotopes of carbon, that is carbon 12 and carbon 14. Both the carbon has the same atomic number, that is 6, but the different atomic masses, that is 2, 12, and 14. And the third example we will take, that is chlorine. The chlorine also have 2 isotopes, that is isotope 35 and the isotope 37. Both the chlorine atom have same number of atomic number 17, but the atomic mass is 35 and 37. Similarly, we have another example of oxygen, that is oxygen 16 and oxygen 17. In that case, both the oxygen has same atomic number, that is 8, but different atomic masses, that is 16 and 17. Similarly, we have the isotope of nitrogen. The atomic number of nitrogen is 7, but we have different isotopes for nitrogen. One is for 14, which having the mass number 14, and another one is 15. I hope you are clear with this concept that isotope having the same atomic number but different atomic masses. This is clear to everyone? Right. Now we are going to discuss
uses of isotope. An isotope of uranium-235 is used as a fuel in nuclear reactors. Carbon-14 isotopes used as carbon dating. An isotope of cobalt-60 is used for the treatment of cancer. An isotope of iodine-131 is used for the treatment of goiter. Now let us discuss about isobars.
isobars. Isobars are the atom which having same atomic mass but different atomic number. It is just opposite to your isotopes. So we can say that isobar of an atom of different elements having same atomic number but different having same atomic mass and different atomic number. So I repeat again, isobars. Isobars are the atoms of different element having same mass number but different atomic number. These pair of elements have the same number of nucleus, or we can say same number of protons and neutrons. For example, we have the case of calcium and argon. In the case of calcium, the atomic number is 20 and atomic mass is 40. So similarly, we have argon where atomic number is 18 but atomic mass is 40. If we see that both argon and calcium have the same sum, that is 20 plus 20, 40. But in the case of argon, it's 18 plus 22, 40. Means if we calculate the sum of protons and neutrons, it is equal to 40 number. Thank you. Have a nice day.